Hello everyone, I'm Li-Hui Tsai, PhD student in National Taiwan University Department of Biomedical Engineering. I'm glad to have a chance to present at this conference. Today, I will share with you a study article. The title is Doxorubicin-loaded PLGA nanoparticle with cationic and ionic polyelectrolyte decoration, characterization and its therapeutic potency. At first, I will talk about this study aim and introduce the material's properties and method used in this study. Also, I will present all types of nanoparticle illustrations. Then, I will show the results and conclusions, hoping everyone will be interested in these few minutes. This study prepared drug-loaded nanoparticle, also mean nanomedicine, then decorations with cationic and anionic polyelectrolyte. Nanomedicine has been used in drug delivery systems, especially in tumor therapy, because it can accumulate in tumors with high vessel densities by EPR effect. EPR is the abbreviation of enhanced permeability and retention. The purpose of decoration was to make nanomedicine more efficient in tumor therapy. It means nanomedicine had pH-dependent release property, high efficiency in cellular uptake, and high efficiency in endolysosome escape. As a carrier of drug, it should have biocompatibility, biodegradability, and low toxicity property. For this reason, PLGA, polylactic glycolic acid, was an ideal option to use to prepare nanomedicine. Doxorubicin, symbol as DOX, endocycline anti-cancer drug, is used widely in several human cancers through two proposed mechanisms, which are topoisomerase inhibition and free radical generation. However, cardiotoxicities and myelosuppression restrict doxorubicin treatment in cancer therapy. Therefore, this study tended to encapsulate doxorubicin in biodegradable PLGA to reduce the side effects. By using double emulsion, doxorubicin-loaded PLGA nanoparticle, symbol as DPN, was successfully prepared. Positively charged polyelectrolyte PEI was designed to decorate on DPN, symbol as IDPN, by electrostatic absorption. Because PEI was supposed to rupture endolysosomes by proton sponge effect. Furthermore, considering cytotoxicities of PEI and serine aggregation, negatively charged polyelectrolyte PAA was implied in the system. PAA, polyalkylic acid, was deposited on IDPN again by electrostatic absorption to diminish the defect of PEI. Now, I'm going to talk about the results. There are included the characterization of DPN, IDPN, and AIDPN. The release profile of these three different nanoparticles suspended in different buffers. Also, nanoparticles were treated to A509, the non-small cell lung cancer cell line, to estimate cell cytotoxicity, cellular uptake, and endolysosome escape efficiency. As the data show in the table, we can find the size of DPN, IDPN, and AIDPN was around 150 to 170 nanometer. It means nanoparticles coated with polyelectrolyte do not make nanoparticle size difference. However, when we talk about the zeta potential, we can find that the outmost polyelectrolytes make the zeta potential difference. Cationic PEI lets IDPN have positive 40 mV, while anionic PAA makes the zeta potential of AIDPN negative, which was around minus 26 mV. Next, go for these three TEM images. From left to right are DPN, IDPN, and AIDPN. Like the table's data, polyelectrolyte coating didn't make a size difference, and all of them were round shape. In this study, using different pH value buffer to mimic different physiological conditions, pH 7.4 PBS buffer was imitates normal physiological condition, and pH 5.5 PBS was regarded as tumor microenvironment. Because the environment surrounding tumor tissue is slightly acid than normal physiological condition. Since acid surroundings could increase doxorubicin solubility, the amount of doxorubicin in pool will increase when DPN was suspended in pH 5.5 surrounding. Therefore, all DPN, IDPN, and AIDPN had a higher release percentage as pH 5.5 PBS. This result implies that all three different nanoparticles, DPN, IDPN, and AIDPN, have potential selected tumor therapy. When we compare the first 8-hour release profile, shown as insert figure, at pH 7.4, there was significant difference between IDPN and AIDPN. However, we didn't find significant difference at pH 5.5. The reason can attribute to that PAA has higher anionic degrees at pH 7.4, which makes doxorubicin have a stronger binding affinity at pH 7.4 PBS. Based on this drug release experiment, AIDPN showed the most potential in cancer therapy. We can imagine when calculation in vivo, AIDPN will release less in normal physiological surrounding, but will release much more doxorubicin once it's surrounded by tumor cells. Again, to pay attention to these two insert graphs, DPN had a higher burst release in the initial few hours. About cytotoxic tests in the A549 cell line, we can find that nanoparticles without doxorubicin, including PN, IPN, and AIPN, as shown in Figure C, had no toxicity in 48-hour incubation. DPN, IDPN, and AIDPN showed dose-dependent cytotoxicity in both 24 and 48-hour incubation, as shown in Figure A and B. In 24-hour incubation, a difference of nanoparticle cytotoxicity could only be observed in 1 molarity. Free doxorubicin showed the highest cytotoxicity in this study, and IDPN had a significant higher cytotoxic effect than AIDPN. When it's talked to cellular uptake experiments, according to Figure D and E, mean fluorescence intensity MFI increased with increasing nanoparticle concentration and incubation time. IDPN has the highest MFI compared to older formulation in all conditions. It could be attributed to IDPN's positive surface charge. However, compared to DPN, the higher uptake of IDPN by A549 cell didn't correspond with the higher cytotoxicity at 1 molarity, which may be due to the more doxorubicin released from DPN within the initial hour, as we mentioned in the previous slide. Explanation again based on the release profile. AIDPN's lowest cytotoxicity may be attributed to its lowest release rate because of PAA retardation. In this slide, we will use fluorescent image to explain nanoparticles' endolysosomal escape ability. Here, the nucleus emits blue fluorescence, endolysosomal stand with lysotrichus emitted green fluorescence, and red represented doxorubicin. In the merged image, yellow represented the combinations of red and green, indicated that DPN, IDPN, and AIDPN were internalized in endolysosomes. Therefore, we can find IDPN was the most capable of endolysosomal escape, because it showed the greatest separation of red and yellow. The abilities of endolysosome escape from high to low was IDPN, AIDPN, and DPN. Nanomedicine was more able to escape from endolysosomes will have much more efficiencies in cytotoxicity, because nanomedicine will not be degraded in acid endolysosomes or ejected by lysosome secretion. PEI seems to be an enhancer in endolysosomal escape. As we mentioned before, PEI's buffer capabilities make it have a proton sponge effect, leading to organelle swelling and burst. Finally, nanomedicine escapes from endolysosomes. In this figure, we can observe that although PAA was diminished the PEI's capability, AIDPN still can escape from endolysosomes. In summary, DPN with negative zeta potential was doxorubicin-loaded PLGA nanoparticle prepared by double emulsion method. After layer-by-layer polyelectrolyte decoration, nanomedicine's zeta potential was dependent on the outermost polyelectrolyte. So, IDPN had a positive surface charge and AIDPN performed a negative zeta potential. PEI was used to decorate DPN because of its proton sponge effect. However, IDPN's positive surface charge might cause cell cytotoxicity and might induce serine protein aggregation. Anionic PAA was then introduced in this drug delivery system to reduce the PEI risk. Moreover, PAA's pH-sensitive property that AIDPN has the most selective tumor therapy potency. In the end, we can make some conclusions. High therapeutic potency doxorubicin-loaded PLGA nanoparticles could be prepared by polyelectrolyte layer-by-layer decoration. IDPN had a slower release rate than DPN in physiological conditions, and had the highest efficiencies in cellular uptake and endolysosomal escape. AIDPN performed the best pH-dependent release profile. AIDPN still retained endolysosomal escape ability and mitigate aggregation risk with serine protein in vivo. Also, AIDPN was the most suitable cancer therapy in these 3 different nanoparticles. Thanks for your attention.